Good afternoon. Welcome. Thank you for coming and here and being part of this new seminar series that we are beginning now, or well, restarting once again this year. This is a great opportunity for you to see what we have been doing in the SafeCop and Enable S3 XL projects. We have actually achieved, these projects have finished, we have achieved quite interesting results, but probably most of you do not know people that have been working, or the team that has been working in the project. And this is important, it's a good opportunity for you to get to know them and to see what they have been working on. And this will actually be what we'll be showing you during the seminars that we'll be having this week, both this one and the next one that will be happening on Thursday. So as you know, well, most of you who know something about my research work, I like to consider myself as an engineer. And that means that I really enjoy practical stuff. I like to do hands-on work, hands-on research. And in the SafeCop project, this was no exception. And well, we can say that the work that we carried out, particularly in the use case, the national use case, we were participating on, which was on vehicular platooning. That was the application we were focusing. There were three pillars, let's say. The first one was obviously research, theoretical research. Second one was simulation, to scale up the results that we had. And then the third one is experimental validation. This is really important in these kind of applications. And to achieve this, we gathered a team of master students, young master students, who dedicated their final year to work with us. And these two students here, both Nuno and Danielle, worked on the robotic testbed. And hope the videos work this time. And there is another master student, which is Guedes, who is sitting over there, who actually also completed his master thesis. All of them completed successfully their master thesis. Their defense was last week. Both of these young men got 18 out of 20. Bruno got 19 out of 20. We have definitely some quality work here. And well, we'll be sharing this work with you and hope that you also enjoy and also get quite excited about it and what we can do next in the immediate future. So thank you, and let's give it to them.
So hello, I'm Nuno. This is my colleague Daniel Almeida, and we will be presenting our work done throughout the last year that is called Autonomous Driving and Platooning Robotic Testbed. So in this presentation we will make an introduction, we will refer to the introduction, the context and objectives, we'll tell you the systems architecture, hardware and software, we'll show you the implementations we have done in the race car, that was Danielle, and the platoon, that was my case. We'll show results from each implementation, and we will show you a safety mechanism, that is the control loss warning, the CLW, that we tested with success in this project. All in the end, we will make some conclusions and refer to future work. So this project was done in line with the European project SafeCop that works with safe cooperative cyber physical systems. CISTER was the leader in the communication work package. CISTER did many things, as the control loss warning, as I referred. We were the ones who implemented in the testbed. We also worked in the framework simulation based on the Robotic and Omnet++. So our work was based on the competition of the autonomous racing competition of cars in the size 1 to 10. The competition is the iPhone 10, as it's shown there. So our objectives were to develop the construction of a robotic testbed, which we should test different algorithms for autonomous racing in platooning scenarios, and also validate the safety mechanism, the CLW.
Hi everyone. Starting with the system architecture in terms of the hardware. This is the diagram, the block diagram represents the architecture of both race car and platoon test beds. Like Nuno said, these platforms are based on the F1 Dance competition, and likewise we use the same type of robot cars they use in the competition. This is an Traxxas RC car on a 1 to 10 scale that we modified with some custom components to support all the components here in this graphic. In terms of onboard computer for the robots, we use an NVIDIA Jetson TX2 to process all the information from the sensors until the actuations upon the car. Besides all the peripherals they have, the decision to use this platform was because of all its processing power it possesses in terms of graphical computation, and especially because it's one of the platforms that is recommended by the F1 10. However, from the Jetson to actuate upon the servo and the motor, we don't have a direct connection, so we have to make a bridge between them. For that, we use a microcontroller based on Arduino called the TC 3.2 that will receive PWM signals from the NVIDIA Jetson and actuate upon the servo and the motor. Starting from the sensors from the race car, which is my case, the main sensor used was the LiDAR. LiDAR is used for measuring the distance from a certain point to another at high precision. In this case, we use an Okuyo LiDAR that has a field of view of 270 degrees with a range up to 30 meters and functions at 40 Hz with high precision. And another sensor that in this case was used for both race car and platoon test beds was an inertial measurement unit. In this case, we use a Razer IMU that has 9 degrees of freedom, composed from a gyroscope, an accelerometer, and a magnetometer. For the platoon test beds, one of the main components was the Z camera. It's a stereo camera that will allow to make image processing and detection for detecting the cars in front of it. One key aspect for the control loss warning, the CLW, was this onboard unit, the OBU, that was used in each 3 of the cars to pass so in order to communicate between all 3 of them. Since we only used a LiDAR for the race car, the platoon cars didn't have a sensor as good as the LiDAR. So we made a sensor board that we will explain further on how it works. But it's mainly composed of 4 rangefinders like this one and the 3 sonars that will allow to detect the cars in front of it. Passing to the software architecture, these 2 systems represent the system of both race car and platoon. In my case, both systems are based on ROS, I forgot to mention, which is widely used in robotic applications. And in my case, we use 4 different packages that ROS provides, being the Actor SLAM, the Adaptive Monte Carlo Localization, and the robot localization that I will explain further on in this presentation. And the package Razer IMU is the package that will allow us to read the information from the IMU sensor. Also in ROS we have our CAD-King workspace, that is our compilation tool to compilate all the scripts we developed for both cars. And other local packages, like for example our URG node that will allow us to read the information from the LiDAR, the raw Shira Python, which allows to have a ROS connection between the NVIDIA Jetson and the TINSI, and RF2O laser odometry, which allows to have odometry based on the LiDAR. Passing to the Platoon software, also taken off. They also have local and exterior packages. In terms of local package, it has the Sonar SRF08, which allows to have the information, to acquire the information from the sonars. Raw shell Python, the same way. And ZPython, where it was developed the algorithm for the image detection. That Python API package will allow to convert the tools provided from Z to Python, and the Vision OpenCV package allow tools for image detection. The package Razor image the same as the last one I explained, and besides all of this, it was used the Darknet, which is a neural network framework that allows that provides
So the Darknet is a framework that is used to train neural networks, and the YOLO v3 YOLO version 3 was the algorithm we used in this case to detect a stop signal. We use a pre-trained based, so it could detect upon 80 objects, of which we chose a stop signal which was kind of useful.
And having the architecture explained, we'll pass down to the implementation. This system here represents the common system of autonomous vehicle. From the sensors in the car, we can have information about the environment and its perception around it, especially its localization. And that's the perception phase. From the perception, we can pass to the planning phase, where from the information gathered, we can plan our trajectory to acquire the desired trajectory to the safest and best way possible. Something that helps both perception and planning is communication between vehicles that allows to give information between cars about its localization and critical information. From acquire the trajectory, you can pass from the planning phase to the control, where we actuate upon the car in its motor and servo to achieve the desired trajectory we want. And based on this system, we'll explain the implementations that were made in both systems. Important part of perception is knowing where the car is in a given map. And the problem with that, it falls into a chicken and egg problem where we don't know which one came first. Because to localize the car, we need to know a map. But to generate a map, we need to know where the car is. To solve this problem, we use the technique called SLAM, which for ones don't know means simultaneous localization and mapping, that allows to generate a map while localizing it at the same time. And it's based on scan matching and grid mapping. In this case, in this testbed, we use Actor SLAM, that's a package from ROS. That's the difference between other packages that implement SLAM is that it only requires LiDAR as input data. So in this video, it's working. I'll show you the Actor SLAM while working. We are manually controlling the car around our oval track. As you can see, the map is being generated, and here this reference system is the localization of the car. The black dots of the grid map are the barriers or the walls of our track, the occupied space, and the blank space is the white, the free spaces of the grid map. This part is stuttering a bit because I wasn't seeing the car. And that's it. Okay. And this was the generated map that we saw. And to prove it was working, the Actor SLAM was working well, we generated an even bigger map of the workspace where we work here at CISTER. And besides our oval track, we have all the undergrad lab map that we generated from the race car. Knowing the map, then we need to localize it in it. From that, we use the sensors from the race car, which, like referred, was the IMU and LiDAR. The IMU gives information about its positioning and orientation, and the LiDAR, in conjunction with this package, gives odometric position based on the LiDAR. However, these two, like in problem where their values will drift over time and they are not as precise as you want. For that, we use a package called Robot Localization that offers tools to fuse this as many inputs as we want. One of the tools that we use from there is the extended common filter, where we receive input data and it will fuse them and provide a much stable odometry information. From the EKF, then we can use it in the adaptive multi-car localization. That's no particle filter based algorithm that will allow to localize then the car within the given map, based on the also information from the LiDAR and odometry. And like the director said, this is a video where we show our adaptive multi-car localization working. Also, we are manually controlling the car till this point. And as you can see here, these are the particle filters from the adaptive multi-car localization that gives an estimation position of the car. And could conclude that it's working actually quite well. Even when racing, making the car running at higher speeds, it was working almost perfectly. Alright. Ending the perception phase and passing to the planning and control implementations. This was a race car. It was intending to participate in the F1 competitions. So we developed 5 algorithms that are based on the F1 competition. The 3 first are based on PID controllers. The first is a simple approach where we just wanted the car to maintain inside the walls of our track. The second one is the explanation given by the F1 crew, where it's supposed for the car to maintain in the center of the track while following a left or right wall. And our curve and line detection implementation, which was our approach to correct problems in the F1 and works by detecting a curve or a straight line and then applying the correct control for it. The disparity extender algorithm is the algorithm from the winners from the competition this year in April. Exactly. That's based on disparities. Simple idea what a disparity is a big variation of distance that from 2 consecutive points, like you can see in this picture. However, this algorithm was not as smooth as you wanted, so we upgraded it, and it's our final and best version of it. To validate and test which one was better, we used trajectory and time as measurements. And here in these 6 videos you will see all the trajectories that the cars were making with each algorithm. The first 2, the follow and the F1 approach. As you can see, it's very oscillating within the track while racing, and it's not an efficient algorithm. Our approach to modify this algorithm, the curve and line detection, we can see a much smoother approach. However, it was not as perfect as we wanted. The disparity algorithm is more robust than the PID controllers. However, we detected a problem that when he detected a disparity, a big oscillation happened. So, as you will see in the disparity upgrade, when they detected at the same point the disparity, the trajectory is much smoother than the previous one. Also, as a proof of concept that these cars can participate in F1 competition, this is a disparity upgraded algorithm while avoiding obstacles in our track. Just some quick results we took from this. This is the average completed life of each algorithm. As you can see, the reliability of both disparity and upgraded disparity algorithm, completing 30 laps. That was the maximum we established. Comparing to the both algorithms. Our curve and light detection algorithm, although it showed a pretty smooth trajectory, the problem with this algorithm was it depends very much on the detection of the curve and the straight line. If it doesn't detect, it will crash over time and explaining this number of loops. And in terms of time, we can see a gradual better performance of over time of implementation of each algorithm given this the time on startup with the car and while already in movement. And the best result we achieved was 4.7 seconds with the disparity upgraded algorithm completing the track.
So for the platooning scenarios, we developed the sensor board. It's constituted by 4 rangefinders and 3 sonars. We have the specifications here, where the rangefinders can measure from 20 centimeters to 1.5 meters, and the sonars can measure from 1 centimeter to 2 meters and have a beam width of 60 degrees. In this platooning, we only based it on this sensor board to detect the car in front. So basically, our lateral control is validated by taking the measurements of the rangefinders and validating with the sonars. How does this work? So we defined 5 states that the car should turn. So the center, center right, center left, right and left. For the center state, we have to validate this sonar and this one. We have to take their measurements and validate the distance within a threshold with the sonar. If it's correct, the steering angle applied will be 0 degrees. If this isn't the case, it will verify the center right or the center left, where each measurement will be validated with the respective sonar beneath. So it will apply a 10-degree steering angle to the right or the left, depending on which one is validated. If this isn't the case also, we have the right and the left, just as it's the same. It will validate with the sonar, the peripheral sonar, and will apply a 15-degree angle. We have a kind of a safe mechanism, so it won't detect an obstacle or a wall and crash. That is, it only can switch states between 2 adjacent zones. So if he's on the right state, he only can go to the center right, and if he's in the center, he can only go to the center right and left. How it works. The longitudinal control, we have a PD control, where our error is the difference between the distance measured by the sonar and our set point of 40 centimeters. That was our safety distance defined. So here we have a video of this platoon case where we can see the velocity is quite slow and the steering angles are quite, they're pretty much defined. You only see a sharp change, exactly. So we made an improvement in this, and we added the Z camera, where we used the YOLO V3 to detect the stop signal, as you can see here. The lateral control is now based on a PD control, whereas the error is the difference between this X coordinate and the middle, that is 640 pixels. By applying this PD control, it will be way smoother, the turning. The longitudinal control, we made an improvement on that, whereas we still maintain the original PD control, but we add another PD control where the error is the difference between the distance in 2 consecutive iterations. As we will see in the results, it has a light change. Here we have the platooning scenario working, where we can see they're way faster this time. And the turning is smoother than it was before. As you can see, I was controlling the first car, so here we have some results from the lateral control. The first graphic is without the camera detection, is only based on the sensor board, and we can see that the heading was around 20 degrees of error. With our improvement with the camera, we could reach a 50% improvement, where the heading was around 7 degrees at the same speed. We tried improving the speed, increasing the speed, I mean, and we could see that the errors were increasing, but only in the last case, where the velocity was 1 meter per second, it had errors superior than without the camera detection. For the longitudinal results, here we have without the camera, the first one, whereas you can see a big oscillation around the 40 centimeters, and it sometimes went really low, really close to the front car. With our improvement, the safety distance was almost always established, was quite good. It only had an overshoot in the initial acceleration, what is normal to expect. So here we have the system of our CLW mechanism. The system developed in the simulation three different types of CLW: the loss of acceleration, loss of brakes, and loss of direction. In our case, as it's more appealing, it's visual more appealing and easier to demonstrate, we tested the loss of direction. So our CLW basically is supposed to monitor the parameters of the car, and through the communications between the OBUs, it will alert if the parameters aren't right. Here we have the Roche cloud that represents our robotic testbed that's based on Roche, where we have the sensor, the planning algorithm, and the gas and steering actuators. We have a host bridge that is also running on the NVIDIA Jetson TX2, and that establishes communication to the OBU through the model message broker. This model is responsible for redirecting information to other models, as the CLW, that is our model for the safety mechanism, and the ETSI, that is the model responsible for establishing the network between the OBUs. Here we have the video of our loss of direction test. In the first case, there won't be the function of the CLW, and we will trigger an error in the steering angle of the second car. As you will see, the first car will turn, and the second one will go straight ahead until it has an accident. In the second part, I'll show you where the CLW is working. Yeah, it would go so on until it crashed. In here, we have the CLW working. So when the first car, we trigger a fail in the second car, and when the first car starts to turn, the second and the third car will receive the alert and stop. So our work, basically, we developed with success our robotic testbed. We were able to implement various algorithms for the race car and the platoon. We also validated the CLW in the robotic testbed, which was quite hard. For future work, we are planning to improve the odometry, approach new control algorithm as the model predictive control. As we have already the combination between the OBUs, we will try to pass more information and make the control through that information received from other cars, and eventually apply this platooning knowledge to drones. Thank you for your time.
Okay, so what were the challenges of implementing CLW?
It was
integrating the CLW with it?
Yeah, it was mainly compiling the host bridge to the NVIDIA Jetson's architecture.
Okay.
That was quite hard because it's kind of unique, and we were working with GMV that could emulate the architecture of the Jetson.
GMV?
GMV, that is a company that worked with us regarding the CLW. It's GMV Skysoft, exactly.
Yeah, so it was not trivial to compile the logs to that particular platform. Okay, very well. But I was curious, in the last video I was actually expecting the second car to follow the first one, maybe with position updates from the front car, maybe I'm mistaken.
Can you repeat? I'm not
Yeah,
following.
So let me understand.
In the second video,
Yeah.
the second video we have the CLW on, and we trigger a fail in the second car steering. So when the first car will start turning, the second car will receive the alert from the first car saying, okay, something is wrong. Okay, actually the second car triggers that alert because it sees, according to the first car, that the steering and heading are incorrect and will stop automatically because it won't be able to turn.
But what was the information exchanged with? So the other guys were exchanging their position and heading and velocity.
On the steering and heading only.
Okay, sure. But and they didn't match its own, the second cars.
The second car didn't match the first car.
And because there is this mismatch, they assume
stops.
there is something wrong and stop. That was the emergency procedure.
And the thresholds are manually calculated, or how do you find the thresholds?
That was developed with GMV, so I'm not sure if I'm allowed to say because it's kind
Yeah,
of
but we
confidential.
can say that in this application, obviously, it was manually found because we had to adapt some of these parameters to fit the dynamics of the robots. Right? So we had to do it manually. Right? I'm right, right?
Yes.
I imagine this is what happened.
Yeah.
Okay.
I still have one. And then, yeah, when you talked about the longitudinal results, can you go back to that slide?
Yes.
I wasn't very clear. So the longitudinal is like a deviation from an axis, a common axis? What it is?
Wait,
Or it was,
you're talking about the platooning? Here?
so next? No.
Here. The results, okay.
Yeah,
Sorry.
Yeah, it was some graphs, I'm not sure.
Here?
Yeah, so I wasn't very clear on what this is, longitudinal results. Is it deviations from the common platoon axis?
It's the distance measured from the second car to the first car in centimeters.
Okay. Alright.
What was the question? Or
No, it's fine, now I understand what it is. So
okay.
I wasn't fully understand what is this longitudinal. So it's distance to the next.
yeah, it's distance to the front car.
And the lateral results were about the next slide.
Yeah, the previous one. The previous one had the headings
Headings.
difference in the same instance
Okay, now
of the
it's
track. Yeah.
Okay. It's curious in the previous slide, there's some kind of oscillation. It seems kind of.
Yeah, in the lowest velocity, the third car to the second car. As the second car has some oscillations, the third car, as the PD control isn't perfect, it will oscillate even more.
I was actually looking at the one in the left. It seems that there's some kind of how should I say?
Out of phase.
Out of phase. That's it.
Yeah, because basically when the second car
90 degrees
accelerates,
opposite phase.
basically when the second car accelerates, the third one isn't already accelerated, so the distance is, the second to the first one is decreasing,
Yeah.
but the second to the third is increasing. So when the second car reacts to slowing down because it's too close, the third car is actually coming closer to the second one, and that's why they look out of phase, let's say.
And you think the communication could help out with that?
Yes.
Improving that?
Yes. The steering and the velocity, both controls.
Sure.
Sorry, maybe you said I didn't fully get it. What exact information is exchanged between the cars?
The steering angle, the steering from the wheels,
those-
and the heading, so the orientation of the car.
Okay. Wheels and car orientation, basically.
Yes.
Okay, so no velocity, no mapping, no nothing.
No, nothing.
Well,
And how do you think that the problem will be addressed if you have a slopey environment? So something.
I'm not prepared for those cases. I actually, as these are low velocities, if we were going up, it probably wouldn't work because the motor wouldn't support that slope. It would be quite difficult actually to establish this platoon in those conditions.
Okay. That is mostly because this was done at a fixed speed.
Yeah.
But I think what the question that was being formulated was not exactly with that point. The point was more what kind of information you can, I believe, right? What kind of information you can pass between the vehicles that can allow you to improve the platooning scenario. Meaning, right now you're using heading and steering angles, right? But
Yes.
you can, what you can
But that is
include.
not used in the platooning scenario. That is
Yeah.
only used to control the stoppage
Yeah.
if it's not correct.
Right.
My
But this
platooning
was done
is
to
only.
test to validate the CLW, right?
Yeah.
But we can include whatever information we want. So right now, and I think I can go ahead and help you about this. Right now we have a licensure degree student that is working, which is Miguel Mestre, which is working on improving precisely these aspects. So he's passing additional information, position, speed, etc. And that will enable us to improve the control algorithms of the platoon.
And the main limitation is extra power to compute, extra time to compute. These are why you stop sending much information.
No, the issue was mostly related to the fact that, well, first we were just testing that particular scenario, how you call it,
The sensor board.
the scenario,
The loss of direction.
loss of direction
Loss of
scenario.
direction.
That was, so those informations were the only one that you needed to do so. And the second was because we did, with the sensors that we had, we couldn't get a precise enough information that we could use, okay, particularly in positioning. So if you are outdoors and you are using a vehicle, you have GPS, but indoors you don't have a GPS, so you have to localize the vehicle in some other way. And this is not trivial, so you need to use some, basically what they
was
did for the
implemented in
front
my
car,
case, implementing
but they
the
had
other
a
cars.
LiDAR in the front vehicle, right? And we didn't have this sensor on the other vehicles.
But they will have matching the maps now not be a trivial task. So.
Yeah, so as soon as now we have some LiDARs, we have also additional wheel encoders that will be deploying, and that means that we can have a precise location or localization to the followers.
Okay.
And with this information, we can obviously even improve a lot these results.
So the main reason why I didn't put more information was because you didn't have the sensors.
Yeah, yeah.
Okay.
Absolutely.
It could be the scenario driven that you really want to explore different scenarios. But
So the idea is that we'll be now using this robotic testbed in many other research perspectives. Some of them being explored right now by NU and Nuno, particularly in the control and networking aspects. So we'll be validating some of the cases we already have working in simulation, but transposing them into the testbed.
One last question. If not, I thank the speaker.